All right. Welcome, everyone. Good afternoon. I hope you all had a fantastic lunch and are ready to dive into my session on network monitoring with real-time telemetry. Before we begin, let me quickly introduce myself. I am Tushar, and I work as a network engineer at Google, focusing on release infrastructure for Google Kubernetes engine. I'm really excited to be here and share my knowledge and experience with you all today. Let's quickly go through the agenda of the session before diving into it in more details. So, we are going to talk about what are the challenges in network monitoring and how it differs from monitoring of software services. We are going to discuss what are the tools available to us, as well as what are the new requirements in the monitoring space as far as network infrastructure goes. Then we are going to take a turn into how the next generation or what's the future looks like for telemetry and where does streaming telemetry fits into the picture. And then we are going to talk about the open config models, which are data models, which allows us to get all of this data. And then we are going to discuss the GNMI protocol, which is the underlying protocol to get this data and where it fits in all the challenges that we will see. And lastly, I'm going to share with you a software stack on how it looks like for network infrastructure monitoring, and then conclude with some best practices around monitoring as well as alerting. So, challenges in network monitoring. In a network infrastructure, you have different kinds of devices, like you have your top of the rack switches, you have your core routers, and you have your firewalls. Fortunately or unfortunately, all these different type of network devices have different monitoring needs as well. For example, for the top of the rack switches, you're only looking to monitor, let's say, just set of interfaces that you are interested in. But for a firewall, you are also looking to monitor what's the flow rate through the firewall, or what's the reject count firewall, and any other security related data. Different type of network devices also produces different types of logs and metrics, which are a challenge in monitoring. And then you have multiple vendors present as well, because you want the best of the breed products. Not all vendors do everything well. For example, you will have a certain vendor that just specializes in firewall or do firewalls really well, and then you will have another vendor that is really cheap and that just fits your budget. Unfortunately, this also means that you would have tools for each vendor, which would cause a lot of operation overhead in your infrastructure. And then you have multiple platforms where your networks are spanned across private cloud, public cloud, and obviously on-prem infrastructure. It is incredibly complex to integrate all this data from different platforms just due to the difference in APIs provided by each of the platforms and then different data formats. As this figure demonstrates, this is a typical overview of how network monitoring infrastructure looks like for most of the companies out here. On the left, you have your network devices, which are producing the metrics. In the center, you have different kinds of collectors, and I'm going to talk about them a bit later. And then on the right, you have your database or any storage solution which would allow you to generate alerts or store data for long-term retention. As far as collectors are concerned, you have three different types, or at least these three types are definitely there. The more important ones is the SNMP one, which is the protocol that gathers all this network monitoring data from devices. Then you have the CLI scripts, where you have a certain kind of script being executed every now and then on the device. This is used mostly for data that is not available through SNMP. And then you have your syslog collector, which is mostly like log streaming to log infrastructure of your choice for analysis. However, it is also used for alerting in certain scenarios. So, why do we want to solve these monitoring challenges, or why fix them when it's not really broken? So when you solve these monitoring challenges, you are really looking in reduction in cost, especially around licensing and operation. It would also simplify your monitoring stack, as you no longer have to deploy a monitoring stack per vendor or per platform. You can have a single instance of your monitoring stack sharded across different regions or different sites, and that will help you troubleshoot faster as well as reduce any operation overhead. This also means that you get more scalability to meet the network demand as well as accommodate the ever-growing increase in number of devices. Let us now talk about SNMP, which is pretty much the protocol that is used to monitor the network infrastructure. This was designed in the late 1900s, and I believe it was 1980s, and hence was designed for limited processing and bandwidth because of the data requirements at that time. It is a pull-based protocol, works over UDP, and it might look really simple to use it because you just need some kind of a tool to just fetch the metrics from the device and send it to your TSDB, but it is often not scalable. This is due to the reason that data provided by SNMP is largely unstructured, untyped, and vendor proprietary, and often also changes between different software releases. And then since it uses UDP, which is an unreliable transport, you also need some kind of active polling by the collector, which also means that you need a strict clock on the collector. Talking about the clock, it also does lack support for source timestamps as well as having multiple connections. To put into perspective or to take a look at some numbers, for any network device, you are looking at collecting about 100K objects per device. So it is really expensive to discover what these objects are, as well as it's very hard to maintain the same pull frequency as the number of devices grow in your infrastructure. Now, things have really taken a turn and requirements have also evolved due to just changes in data generation volume and in general infrastructure improvements. Operators these days are now looking for some kind of a SDN or a centralized control solution just because they want greater flexibility and control. They are also looking for their traffic engineering solution to respond in order of minutes and not hours. And hence, you really need a real-time feedback loop from your monitoring systems. Then operators also want to just troubleshoot using the dashboards or just the metrics rather than diving deep into the logs and trying to figure out what went wrong. The dashboards that should be provided to the user should be verbose enough to provide this information, but care should be taken that you are not overwhelming the operator with lots of data. And lastly, you are also looking to predict and remediate faults in advance to detect potential issues in order to maintain your SLO as well as reduce your downtime. So how do we reimagine telemetry to meet these new demands and also address the challenges that we saw earlier? Any telemetry solution should answer questions like what kind of data has to be collected, how often has to be collected, how it will be transformed, and how and where it will be stored, and in fact, how long it will be stored for. For example, my telemetry should be able to answer if a link is down in the system or not, and if it is down, why it is down. What is my uplink utilization across the particular site or across the entire network infrastructure I have. Now let us talk about how the actual monitoring system would look like to handle the requirements. First, you need to reverse the flow. Instead of a pull-based solution like SNMP, it should be a push-based solution with continuously streaming of data. That means you would eliminate any need for a polling interval as well as any CPU spikes that might happen because of the continuous polling that you're doing on the device. Secondly, it should also have some kind of APIs to select which data to stream. I don't want my network device to stream all of the data, and I should basically process what I need. I also want to avoid making changes to the network device configuration just to select what kind of data I want to stream. Third, it should have some capability to incrementally stream updates with some refresh capabilities. What does it mean? For example, boot time metric. This metric does not change often. Once the device boots up, it is fixed in a timestamp and won't change until the next reboot of the device. I don't want to stream this metric every 1 minute or every 30 seconds. Rather, I want to stream it once and then refresh this metric every 10 minutes or every half an hour. Fourth, the data schema that is being used to store this metric should be fit for storing in TSDB. For example, the telemetry should avoid generating string metrics since not all TSDB supports string metrics. And the fifth is the data model should be consistent across multiple vendors. For example, if I'm fetching CPU utilization from my monitoring, my request response should not change or should not depend upon the platform or the vendor I'm using. And lastly, the underlying transport should be efficient and secure, like gRPC or Thrift. SNMP supports encryption, but it adds like a lot of overhead since it's done in user space. So let us now move on to OpenConfig. What is OpenConfig? It's an industry initiative to develop vendor-neutral data models, both for network configuration as well as operational state. So instead of having different data models for configuring the device and monitoring, there is just one single data model and it is used to do both of these tasks. It is written in YANG, which is yet another next generation, and it supports a variety of devices from switching, routing, as well as Wi-Fi access points. In its current state, majority of the new platforms support retrieving data through these models, as well as they are very fairly stable. It also has supports for extension for vendor proprietary stuff, so you can still so vendors are still bound by it. So when you use OpenConfig models to retrieve data, you no longer have to build pipelines per vendor or per platform or per roles. Everything will be ingested by one single data pipeline and will be transformed and put into the database of your choice. The models themselves are protocol agnostic. So for example, you can use gRPC, which is protocol buffer over HTTP 2.0. You can also use netconfig, which is RPC over SSH, but with encoding of XML. This is typically used for machine-to-machine communication, though. Some small differences between how SNMP and fetching data via streaming telemetry differs. With SNMP on the left, you can see that the client has to reach out to the device and it will get the data. But with the collector, you reach out to the device once and it will stream all the data. And then due to this nature, there are benefits which we'll discuss further in the next slide. So what are the benefits? First is you get better coverage while using streaming telemetry, since you no longer have to sample at intervals. The data is continuously streamed from the device. Since it is also push-based, it can be made to be done at a higher frequency and can offer near real-time monitoring, which means your feedback loops are really fast. It is event-driven, so information is immediately available as conditions are met, unlike SNMP, where you have to poll for conditions in order to see if they are satisfied or not. When compared to SNMP, which uses UDP, it uses a reliable mode of transport that we are going to look for in the next few slides. And lastly, since all the data that is being fetched using streaming telemetry uses common models, the data can be normalized across multiple vendor or multiple platforms. Talking about the protocol that is commonly used to fetch this data is GNMI, which stands for gRPC Network Management Interface. It was developed by Google initially, and since I think it has been handed off to CNCF now. But yeah, that's the protocol for configuration manipulation as well as state retrieval. Like with everything with Google, it uses protobuf for service definitions and encoding for payload. And it can be used with data that is not even Yang modeled or open config model. So it's again model agnostic. As I said, it's built on top of gRPC, so you get all the nice benefits of gRPC like bidirectional streaming, health checking, and authentication, pluggable load balancing. But the most important thing here is the set of RPCs that it provides. And for the purpose of monitoring, the RPCs that are of interest are capabilities and subscribe. So for capabilities, it basically tells the collector what kind of encodings and models are supported by the device. For subscribe, that's just like a streaming RPC to send data to the collector. The other two RPCs, get and set, are used to retrieve and manipulate the state respectively. So GNMI can work in two modes, dial in and dial out. Both of these modes are defined from the purpose of, or from the perspective of the network device. And in both of these modes, the data is always streamed from the end devices. So how does these modes differ? In dial-in mode, the collector has to reach out first to the network device, while in dial-out mode, the device will reach out first to the collector. So which to use and when? So dial-out is usually loved by SecOps people, as you no longer have to poke holes in the firewall to allow someone to connect to the device. But with dial-in, you get a single channel for telemetry as well as router configuration. So you save on some bandwidth. I would also like to highlight what is the current tooling in this open config space. So first is the data serialization, which is, again, on the configuration part of network devices. And I have never had a need to use them for monitoring use cases. Second is your telemetry collectors, which are like kind of open source collectors that you can use to retrieve monitoring data from variety of network devices. In this, the Telegraph GNMI plugin is fairly stable and works across multiple platforms and vendors very nicely. The third one is if you want to author your own Yang models for whatever reason, you can follow their style guide and checker. And then the last one are network management system. And these provide like a client and a server libraries to test GNMI data or play around with gRPCs. Talking about the software stack, this is how it typically looks like. It's not different than usual monitoring of services, but I would still like to visit in brief. So on the left, you have your telemetry or the device producing the telemetry. In the middle, you have a set of collectors, and on the right, you have your visualizing agents or anything that the user deals with usually. So as far as collector is concerned, I've shown Telegraph here, but it does not have to be Telegraph. The thing with Telegraph is, since it supports GNMI across multiple platforms, it would just work. You can just plug it in your infrastructure and it would just work, and then you get all the nice benefits of a Telegraph, like transforming data into different kinds of outputs, which in this case is Prometheus and InfluxDB. Once these outputs are there in the TSDB of your choice, they can be retrieved using Grafana or any other dashboarding service of your choice, and then you can also set up alerts using Capacitor via the same method. Some best practices around monitoring. So with network devices, raw metrics are mostly not useful. For example, I'm hardly ever interested in how many bytes went through the device in the last, or how many bytes, what's the raw number around the bytes that went through the device. What I'm mostly interested in, how many bytes went through the device in last 1 minute. So rate is mostly the useful metrics with network devices. And if you're storing a raw time series with just raw numbers, you would have to compute the rate while you're retrieving them. My suggestion here is to always pre-compute the rate rather than computing it on the fly during retrieval. And you should also compute it at different step intervals, like rate every 1 minute, rate every 5 minutes, and rate every 15 minutes. it would really help the operator try to figure out what the problem is. Next is the cardinality challenges, which is always a challenge, whether it is monitoring network devices or whether it is monitoring software services. High cardinality can provide you with a lot more information, but it also affects performance, since every label is basically a new time series metric. For network devices, at a minimum, you at least want 3 labels attached to pretty much every time series that you have. So you want your role, basically what role is being served by the device, like top of the rack, firewall. You want the site, where does the device belongs to, and then the device name itself. And then you will have additional labels like interface name, but that would vary from what kind of metrics is being generated. And lastly, you also want to monitor from at least 2 different sources if you have the budget for it. This would really help you to identify where the issue lies and avoid discrepancy, especially with larger networks of 1,000+ devices. And to add on top of that, you should also make sure that you add the monitoring source as a label into your time series. Some practices around alerting. Your alert should be topology aware. What do I mean by that? For example, if my top of the rack goes down, or if my server goes down, or if the link between both of them goes down, I don't want multiple alerts. I only want one single alert. Another example is if my entire site goes down with 100+ devices, I don't want 100+ alerts or 100+ alerts paging me. I only want one single alert, right? So you really want your alert to be aware about the topology that is being served by that particular site. Secondly, you want to alert on symptoms and not causes to avoid alert fatigue. For example, I don't want to alert on high CPU utilization, but rather alert on network slowdown, and then the operator should decide whether if it was due to high CPU utilization or something else. Third, you should have some kind of monitoring solution to detect chronic alerts. What are these chronic alerts? So we often have some alerts that are generated that happens to live for a short duration. Like by the time you get to them, they would auto-resolve themselves, and then sometimes they're just triaged by different individuals, so you really no longer have a correlation between them. So you really should have some kind of a different monitoring solution to detect if an alert is happening repetitively over the last, let's say, 1 month or 2 months, and make effort to triage it. So to conclude, I just want to highlight how all of it fits together, including configuration as well as telemetry. So on the left, you have your telemetry collectors, and then over here you have your multi-vendor devices. All of them are exposing the same data models. These are being consumed by your collectors and being transformed and then being used by your traffic engineering systems or dashboards and alerting systems. They are also being used to program the devices using some kind of an intent API using GNMI. So you have one single model that basically does all of the things. And that's it from my side. Any questions that you would like me to answer?
Oh, man, we got hands already up. I love it. We'll start with you.
So you mentioned topology-aware alerting. Do you have a way to detect topology programmatically and put that awareness in, or do you have to define it proactively?
Do you have to detect topology? Is these?
Yeah, so you cannot store it in your alerting system. You need to have a different model to expose that topology. And then the way I do it is, we have a different system running that would automatically silence the alerts. So they're at the cost of some delay. So let's say if an alert fires now, the paging won't happen until like next 2 or 3 minutes when all of the alerts from a single site have fired. And then that service would basically silence the alerts based on the topology. So like I don't want all the alerts of the TOR, right? Or I want all the alerts that are from the upper layers. So only that alert would be kept.
But how do you store topology?
How do you store it?
It depends. We use UNM to model that topology, and it's kind of a hard problem to do. But for campus enterprises, it's fairly simple. You can also do some kind of a role-based topology, like you have the role of your core, you have the role of your border switches, you have a role of your top of the rack. So just by looking at the role, you know if all of these three roles fire, I only need to generate alert from the border router, because that's the first point of entry of traffic.
Great. Any other questions? I'm going to look up top real quick. Up top, anything up there? Anything back? Right here?
Yeah, it seems like there's a lot of benefits to streaming telemetry. And in fact, I think there was a presentation a couple of years ago, like S&P is dead, but as far as I can tell, 99.9% of network monitoring is still S&P. Why is that?
Why is so much network monitoring S&P?
I don't know, maybe network engineers are just paranoid people and they don't want to change things. So
There's an XKCD comic that probably explains this.
yeah, I mean, it's, as I said, it's hard to justify migration when it's not broken. But from what I've seen in the industry, all the new protocols that are coming in, or the next set of design, they are not even supported by SNMP. Vendors don't want to evolve that space anymore. So sooner or later, maybe 3 years, 4 years down the line, you will have to migrate. So, yeah.
Down here.
I mean, a related question, how many devices at Google are streaming telemetry versus still the old?
Oh, everything is streaming telemetry. So I don't work with
So the
production
question is how
backgrounds.
many devices are streaming it, yeah?
Oh, like the raw number of devices?
Well, no, just in general.
I mean, as far as I know, 100% of the devices is streaming telemetry. But unfortunately, I don't work with prod backbones. I work on a different release infrastructure, and all of our close to 500 plus devices are streaming telemetry from day one, apart from like maybe 10-ish or something. But production network is entirely streaming telemetry.
I think one right here.
Just wondering, is it completely separate monitoring for network layer? Is it completely not connected to application layer, to all other Google production layers?
Is the network layer completely separate?
In what terms, like, is it separate? Like,
Alert in monitoring like this. You describe it good idea for network monitoring, but in some cases it does not make sense without connection to some application issues, to some other things.
no, I think it is mostly disconnected. So there is a boundary, and that boundary is unfortunately fortunately not application. Otherwise, a network engineer is going to get a lot of pages. So the boundary is mostly hardware layer. So let's say if a server goes down and the issue is with the network, you will only get one alert. So that kind of correlation is there. But if there is an impact on an application, which there would be, then the application team would get separate set of alerts, and it's their job to correlate that it was a network issue.
Why we need two different systems? That's not logical.
Like
Why
what?
two different systems?
Sorry?
Why two different
You have
systems?
two different systems, one on application layer, another on network layer, and you have actually two sets of the alarms. Why? It's not logical.
It just won't work at that scale, right? So because we have this concept of cells, and usually the way production services are run, there is redundancy built into pretty much at every single layer. So I would just say for scaling reasons, it would just not work out, because you don't even know at times if, let's say, a particular rack goes down. Application owners don't know which rack their services are running in. All they know is which cell they are running it in.
Did you try to share network layer information with application layer somehow?
No. So it's all handled by, it's all abstracted, I would say.
Any other questions? I think we have time for one more. Yep, right in the middle here.
You talked about pre-computing rates, and I was wondering at what level, like, if you're doing it near, very near the edge, you might have many of them if you're using like a memoryless rate computation explanation, okay? Or do you do it later where you're just aggregating that all and then computing?
So at what level are you pre-computing rates? Layer.
So like for interface utilization, we just pre-compute the moment the metrics is ingested first. So our ingestion pipeline, so let's say I get the metric from the device, we will transform it into the labels that we would like, and then just pre-compute the rate over there. So there is some kind of caching there as well just to compute the rate, but that's pretty much it, and then it sends all the way down to your database.
Awesome. Let's do another big round of applause for Tushar. Thank you so much. It's awesome.